Dobar dan. Good day, everyone. Um, my name is Aleksei. I'm happy to be here, and today I'm going to share some insights on topic I'm passionate about, which is decentralized finance, math, and algorithms. But before, let me tell you a bit about myself. So, I've been working in machine learning and data science for over 8 years in several Russian companies. So in Maxima Telecom, I led a team of machine learning researchers, sorry. However, my biggest professional growth happened at Avito, which is, by the way, the largest classified ads website in the world. There, I trained some machine learning models to make search better. And recently, I made a big career change. I left Avito to focus fully on quantitative, sorry. And together with a team of like-minded people, we create high-frequency trading robots and explore advanced algo trading. Today I'm going to give you some building blocks for the system, trading system for DEXs, and this system is going either to make your money or lose it all. Unfortunately, I cannot provide you any guarantees. But let's start. So, have you ever wondered how prices on different exchanges match? Not so long ago, while being a good engineer, I was not so knowledgeable in finance, and so I used to think that there is some magical process that synchronizes prices across exchanges. However, the reality is a bit different, and it's called arbitrage. Well, this is a very basic natural law of economics. When something is cheaper on one exchange and the more expensive on the other, arbitrageur buys on the cheaper exchange and sells on the more expensive market, essentially pushing the prices closer together and leveling them off. So this is the beauty of economics, it balances itself, and arbitrageurs play the crucial role in many financial markets because they provide liquidity and enhance market stability in general. So the design of many online and offline exchanges intentionally includes their presence to fulfill this role. Now let's discuss how we can apply this concept to decentralized exchanges. But before, we need to discuss some key challenge with traditional centralized exchange arbitrage strategies, and this is non-atomicity. You see, when you are performing an arbitrage trade on a classical centralized exchange, you need to perform several separate steps. And this is a risk because you may face a problem of partial execution where you can buy on one exchange but cannot sell on another because like the price has changed or the order book is empty or you face some unexpected network delay. And this happens all the time on centralized exchanges. And this is why classical arbitrage is risky, and this is why we need to be creative and we need better strategies. Now let's revisit what a DEX is, and I will focus specifically on Uniswap v2, and some of you might wonder, isn't Uniswap v2 like outdated and less effective? And while it's true, it's also true that there are a lot of forks of Uniswap v2 still being used right now. And what's more important for us, that Uniswap v2 is very simple, and we can like grasp a general concept on Uniswap v2, and then I will like explain you how we can extrapolate this knowledge to more complex DEXs. So basically, unlike centralized exchanges, Uniswap v2 uses automated market maker concept and liquidity pool model. And the liquidity pool is just a collection of funds provided by the users, and users known as liquidity providers. Those liquidity providers deposit some pair of assets into the pool and get liquidity tokens in return, and any time they can redeem these tokens for the pair of underlying assets plus some portion of trading fees. Uniswap v2 uses the constant product formula, which is xy equals k, the product of quantities of the assets inside the pool equals constant, which is like this formula ensures that the balance is present in the pool. So when a user wants to swap one asset for another, They interact with a smart contract which calculates the exchange rate based on the reserves, and then swap adjusts these reserves, and swap process ensures that this constant product formula holds. So in practice, DEX can be seen as the collection of such pools, which is just smart contracts, or to put it simply, just classes in Solidity language. For me, it's the same. And now we can state the main advantage of DEX arbitrage, which is atomicity. So we can illustrate this concept on this Solidity code, but I will explain you. We can see that we have here an arbitrage contract with arbitrage function defined, and what's happening here that we, before doing any transactions, we check our balance before, then we perform some swaps, like we swap USDT for WETH and WETH for USDT back, and after we check our balance again, and in the end, in the last line, if our balance after the transaction is not greater than the balance before, the whole transaction reverts, and we pay the gas, only the gas, meaning that this means that our risk is limited to only gas fees, which is a small predictable amount compared to the trade size and the profit. And this is what makes DEX arbitrage like low risky strategy compared to classical arbitrage. Okay, and now let us review the general architecture of the system that exploits these price differences. And so our system interacts with a global P2P blockchain network, and our system itself is a trading server which runs two separate processes. One of them is a blockchain node, and the other is a price discrepancy detector. We can also call it a strategy. So the blockchain node keeps our system updated with the latest state of the global blockchain network. It pushes latest state changes and transaction data, while the price discrepancy detector is like a lightweight program. It's written in some fast language like C++ or Rust. We prefer Rust, by the way. And for each and every one piece of data, piece of information, this program must calculate optimal arbitrage transactions and send them back, and it must do it so fast that these transactions will be included in the next block. So the key challenge here is that we perform heavy calculations there. This is a CPU-bound program. We need to calculate the price like 1,000,000 times per second, and this means that we cannot do this on-chain in Solidity. We must move this calculations to our application side, and this means that we need to copy the price calculation logic from DEXs to our application. And this is a big challenge because, like for Uniswap v2, this is a very simple logic, 4 lines of code maybe, and for Uniswap v3 and similar, it's like about 1,000 lines of code, and our team has spent a few months just porting this logic to our application side. Okay, and now let's discuss the core component of Uniswap v2. I call it pricing function. This is just my interpretation, but this is like get amount out function, which calculates the amount of output tokens depending on the input tokens. You can see the formula in the top of the slide, and this function has one important property, which is nonlinearity, meaning that as you increase input amount, you get your average price becomes worse, and this means that you get less output for each additional unit of input, and this is very important because this is done on purpose. This behavior emulates some price impact behavior that you can see on the centralized exchanges. Like on centralized exchanges, when you place a large order, it moves the market price. Here we don't have orders, but we need to like copy this behavior somehow. This is like the emulation. We can see this as emulation of price impact. Okay, and now let's discuss how we can check if we can profit from two Uniswap v2 pairs. How we can determine this. Let's assume we have two Uniswap v2 pairs with given reserves, and we want to check if we can profit from like swap from USDT to WETH and from WETH to USDT back on two different pairs. And in order to do this, we need to construct a profit function, which is just a difference between amount of tokens we get in the end and the amount of tokens we have before the transaction, and plus the gas fees, but let's assume this is a small constant compared to the amounts and the profit. Let's ignore it for now. So this is just the difference between the tokens we have after and before, just two nested get amount counts, first for the first swap and the second for the second swap. And we need to notice here that this expression, it depends on A. So in order to prove that we have a profitable arbitrage opportunity, we need to find A such that profit of A is greater than 0. This difference must be greater than 0. And in order to, I suggest to approach this problem by looking at the graphs. So here in the left part of the slide, we have the plot for get amount out function applied twice. So this is the dependence between the input amount of tokens and the output amount of tokens after two swaps. And the right plot is the graph for profit function, which derived from the left plot by subtracting the initial amount. And the initial amount is this red line. So we can see that this is somehow similar to 45-degree clockwise rotation. And the maximal profit, the point of maximal profit here shown as a red cross. And let's pause for a second and think what we have discovered. As we increase our input amount, our profit grows up until some point, and then it starts to decrease. And this basically means that at this exact point, the prices became equal. So as we increase our input amount, we push the prices closer together. Then at some point they're equal, and they become to diverge. And this means that we're losing money. And we also we can calculate this using formulas. You don't need to understand them actually, just knowing about their existence would be helpful. But we can like take our profit function, which is this, and find its derivative and solve the equation derivative equals to 0 and find this formula, which is this amount and the point of maximal profit. So are we done here? Like we can apply this formula and the problem is solved? Not quite. Let me explain why. But before this, let us introduce the notion of a path. A path is just a sequence of swaps. We've seen already an example of such path before. On the previous slides here, there is another example, like we swap from USDT to BTC and then from BTC to USDT back. This is two swap path. And so we want our path to consist of various DEX protocols, like we want to buy on Uniswap P2 and sell on Uniswap P3, because statistically arbitrage opportunities appear more often on such paths. But the bad news is that the price calculation logic for these DEXs is much more complex, and it cannot be expressed in a simple formulas. And the good news is we can walk around this, and because we can assume some fundamental economic property for each DEX, which is the price impact, meaning that the shape of the curve of the pricing function we've seen for Uniswap V2 will be similar for these DEXs, which means that our reasoning about the existence of single maximum is still valid, which means that we can solve this problem numerically. And the algorithm that's going to solve this problem is called golden section search. You can ignore the code for now because we have a beautiful animation that illustrates its principles. But like golden section search or GSS is similar to binary search you might be familiar with. It iteratively discards a part of search space, narrowing the range which contains the true point. And the great thing about it, it converges very fast logarithmically. And what's also great about it is that you can set the precision you want, where we want to stop. And in practice, we use a precision of few dollars here, and it converges at maximum at 20 to 30 iterations. So now we have, finally, we have a universal formal criterion to check if we can profit from a given arbitrage path. But do you remember that we said, let's assume we have a path. How do we get those paths in the first place? And let's remember that the classical definition of arbitrage is a cycle on the graph of tokens and pairs. Here is the example. So this is just the loop, and any arbitrage path is just the sequence of those tokens and arrows, pairs, which starts and ends in the same node. And in order to calculate these paths, we can like apply plenty of algorithms, but we used the most primitive, simple DFS, which is like checking iteratively all the neighbors recursively. And this is the example of how it can be implemented, but as always, you don't need to dive into it. So what we need to understand here is that this is a very heavy computation, exponential in complexity, but the good news is that graph structure don't change frequently. We can compute it rarely, like once per day or once per hour will be enough. And finally, we've arrived at the point where we can bundle together all the components into the generalized in the single arbitrage algorithm, which is the following. First, before running the main loop, we need to compute the paths using DFS and keep them updated. And then the main loop starts, which is we need to first receive a price update or state update, like the new piece of data. Then we need to iterate through all paths and calculate the optimal amounts for them using formula if it's Uniswap P2 or GSS if it's not Uniswap P2. Then we select one or more optimal paths and send the transactions by calling our arbitrage contract, and then we repeat the process. But let's now discuss why all of this won't work. At least it won't work in as is vanilla setup. And that's the main reason is you are not the only arbitrager on the network, and all other market participants, they know the same things. They know how to calculate paths, they know how to calculate amounts, and some of them even have some unique infrastructural advantages, like they have partnership with validators, and if you will fight with them for the single opportunity, for the same opportunity, with high probability they will win and you will lose. So our edge lies in being just smarter. We need to tune our framework somehow and to be creative, and that's where the real art begins. But unfortunately, this art falls out of the scope of the introductory talk, but I will like give you some ideas and research directions in the next slides. Let's first discuss performance considerations, because our search space is enormous. If we will try to calculate all the paths for the large blockchain like Binance Smart Chain, you will get around like 10 billion of paths. And this is a very large number. We need to reduce it somehow. So the basic techniques are you must limit cycle lengths, you must limit algorithm runtime, and we can be more smart. For example, we can calculate the upper bound for our profit function that does not depend on A, and using this we can like discard unpromising paths very quickly. We can apply some manual rules that will discard some paths using historical statistics, for example, liquidity statistics and recent activity statistics. And since I am a machine learning expert, I would naturally suggest to use machine learning here. We can apply some high performance models and try to predict something like the existence of arbitrage opportunity given such update. And we can prioritize these paths using the output of this model. So far we haven't discussed what happens when multiple traders submit their transactions that are going to exploit one opportunity. And basically, obviously, one of them wins and the rest are getting reverted and they pay the gas. But what determines the winner? And this depends on the network you're trading on. And I would classify these networks into three main types. First of them is networks like Telos EVM, where you cannot set the gas price or gas tips, so the speed is the key, and this is just the rest. Whoever first submits the transaction wins. On the other hand, we have more traditional networks that operate under more traditional rules, where something that I call gas auction takes place. So you just set the bid, and you like pay for your priority. So the highest bid wins. And among these networks, we have a subset which operates under slightly different rules because of the existence of flash bots and MEF builders, which allow the rewards to be free. So you don't need to pay for your rewards, which means that this shifts the risk-reward ratio for such networks even more, and this leads to very aggressive bidding. And because of this, we prefer not to trade on such networks. But as you can see, most of the networks require you to place a bid in order to participate in gas auction. And here are some typical strategies we can use for this. We can start from the most simple one, which is just place a constant, or place a multiple of base gas price, or place a percentage of your expected profit, or which is more smart, you can place a multiple of your competitors' bid, because you need to outbid them. You can like monitor their bids and place the bids that depend on their bids. And since I'm a machine learning expert, I would naturally advise to use machine learning here. We can try to predict winning bids using machine learning models, or we can, which is more smart, we can try to predict the probability of winning, and we can then adjust our bids using this probability, and we can select the more promising paths to using this probability. And the last thing I want to state here is that we don't even need our own money to perform DEX arbitrage, because we have flash loans, and the flash loan is just an ability to borrow large amount of crypto, provided that you will repay this loan inside the same transaction. And this means that we can perform high volume trades even without having large amount of capital in our account. And this is what makes DEX arbitrage not only low risk strategy, but like low capital requirement strategy. And speaking of our financial results, after some careful consideration, we decided not to disclose most of them, but you can see that even on such small, moderate liquidity network, we've managed to convert $5 into $5K, which is 1,000x multiplier. And this is basically it. That's all I wanted to say. Then in conclusion, I want to say that like DEX arbitrage is hard, but it's possible for individuals, not large companies, to do. And I'm open to any questions you might have.
Do we have questions? Yes. Okay.
Yeah, thanks for the talk. I have a quick one. So, do you consider some specific types of liquidity pools? For example, you arbitrage only on high liquidity pools like VIF, USDC, stable pools, or it's not something you consider? You just do something else to pick the pool you will arbitrage.
Well, we take this into account when just by solving these optimization problems, like because we select the more promising paths using some rules. But as I said, we cannot like brute force all this space, and we need to restrict this, like reduce this search space somehow. And this where we can apply we can take liquidity into account, because when we need to traverse more promising paths at first, and here we can rank them using like liquidity statistics, or because like high liquid pools arbitrage opportunities appear more often on highly liquid pools. This is the answer? Yes.
Yeah, you mentioned BSC is a chain with lots of pools and capital. And in your table where you showed your results, there was no BSC. Are you recommending to just avoid?
No, I've mentioned that we prefer not to trade on such networks because of aggressive bidding. It's our choice.
Thank you. Anyone else? Yeah, you.
How important is gas optimization in the arbitrage contract?
Well, it's important. On some networks, it's even more important to optimize not the gas, but the cold data size, because it costs more than the gas. And I know the examples of contracts where guys like, instead of passing just the arguments to the function, they passed just row U256, just bytes, and then inside the contract they sliced it back into these variables. So this is important, and in some cases it's even more important. It's important to optimize the amount of gas you pay in case of revert, obviously.
Thank you. And we have time for one more. Yep.
Yeah, I'm just very curious about like the probability function, right?
Yeah.
Like, do you just take like normal distribution, or do you have like any kind of proprietary method?
You can just take any gradient boosting library and train machine learning model to predict this probability. Well, that's what I suggest here, at least. What's cool about this, that you can optimize your gas bids using the same model, because your model, you can like pass the gas bid you want to set as the feature to this model, and you can then optimize the gas just by maximizing this probability. So to be short, I suggest not to model this in closed form using formulas, but I suggest to model this probability as a machine learning model.
Oh, so it's more of like a heuristic, right? Than like a mathematical foundation behind all of this, right?
In some sense, all machine learning models is heuristics. Yes, are heuristics.
Great. Thank you so much. Anyone else? I guess that's it. Thank you very much once again.